Okay, the product rule when finding derivatives. So this is lesson 2.3. They've given it represented like this. The function. If the function is made up of one function multiplied by another function, then the derivative of that is the derivative of the first function. Okay, derivative of the first function. Notice we have f prime x times the original second function plus the original first function times the derivative of the second function. Okay, so when we're going through the product rule, and this becomes type of a symmetrical equation if we have more, say we're being multiplied by a third product. Okay, the idea is the same. We derive the first function, then multiply by whatever's left. So if there was 3 of them, we prime this, then multiply by whatever left. Then in our second one, we prime our second function or derive our second function, multiply by whatever's left. And if there was a third one, we would derive that and multiply by whatever's left. Okay, so we have to find the derivative of each of them. We split it up into addition type question. So we'll do our first question here. It's the first example in your book. Is it? No, second example, sorry. Example 2. They've given us h at x is equal to x squared minus 3x, x to the power of 5 plus 2. Okay? Now, remember, what we did in the last lesson is we made this a sum question. Right? We decided to distribute these terms. Once we distributed and simplified, we made this a sum function, but this is a faster way to do it. Instead of going through that process, think of this as our first function. So this is our f at x, and this is our g at x. Okay? And what we're going to do is we're going to find, so h prime x, we're going to derive the first function. So inside these brackets, well, derivative of x squared is 2x, and derivative of negative 3x is just minus 3. So that's f prime. I'll write that below. That's technically f prime x. And then we still have our original g at x, which is x to the power of 5 plus 2. So that's times our original g at x. But now we have to add our original f at x, which is x squared minus 3x. So that's our original f at x times our g prime. So our derivative of g at x. And what's inside those brackets? Well, the derivative of this becomes 5. Remember, our exponent comes down, becomes our coefficient, x to the power of 4. And because this is a constant term, it's just 0. So that would be the derivative of that. Okay. So what we're going to do here is I'm going to distribute a bit and collect my like terms. Okay. So now that I've done this, we can distribute our terms. I can multiply the 2 by this and the 2 by that and the negative 3 by both terms, because now we're dealing with h prime x. So 2x times x to the power of 5 gives us 2x to the power of 6. 2x times 2 is 4x. Negative 3 times that is negative 3x to the power of 5 minus 6. And then because there's only one term here, I just multiply that term by both of the terms inside the brackets. So plus 5x to the power of 4 times x squared gives us 5x to the power of 6. And this gives us negative 15x to the power of 5. So what I want us to do is collect our like terms. We have x to the power of 6. We have some coefficient x to the power of 5. And then we have x to the power of 1 by itself and a constant term by itself. So we're going to collect our like terms. 2x to the power of 6 plus 5x to the power of 6 gives us 7x to the power of 6. Negative 3 and negative 15 gives us negative 18x to the power of 5 plus 4x minus 6, because those are all like terms. So that would be our derivative of our h. h at x, this is our h prime x, or a derivative of h at x. Becomes this function here. And if you notice, we had to go through the priming the first function times the original, and then priming the second function times the other original.